Hello, I'm Nicolene Weil, and I'm a solar physicist at NASA's Goddard Space Flight Center. What we're looking at right now is imagery from the Solar Dynamics Observatory. All of the dynamics and activity that's going on in the solar corona, the sun's atmosphere, which is what I study. What we're seeing here is a filament, and it looks very dark, and it looks like it's actually maybe even on the surface of the sun. But we can see as the sun rotates around that actually it's suspended high up in the atmosphere away from the surface. When viewed from this angle, we call them prominences. This material is held up in the corona by twisted magnetic fields. We're looking at the solar corona in extreme ultraviolet at 171 angstroms, which is a wavelength that our eyes cannot see. My favorite thing is all of these magnetic loops that you can see on the sun, how dynamic these magnetic loops are, just telling us how much change and evolution and activity there is on the sun at all scales. We can see on the northern part of the sun that a prominence rotates onto the disk of the sun and then it erupts in a giant coronal mass ejection. And all of that magnetic energy and all of the plasma that was trapped on those magnetic field lines launches out into the solar system. We're watching the sun rotate right now. This is one of the basic features of the sun, and it takes about a month for the sun to rotate fully around and to see the same spot on the sun come back. We're seeing the sun rotate so quickly in this movie because it's time-lapsed. When the sun jumps around, that's actually the Solar Dynamics Observatory moving around and pointing in different directions. Sometimes they have to point away from the sun so that they can calibrate their sensors, the cameras. When we see the frames go dark, that's eclipse season, so that's when the Solar Dynamics Observatory, which is orbiting the Earth, goes behind the Earth, and the Earth is between the Solar Dynamics Observatory and the sun, and so the Earth eclipses the images. These really bright spots, called active regions, have concentrated magnetic field and concentrated heating because of this extra magnetic field and the extra energy due to it. There are more active regions during solar maximum and fewer active regions during solar minimum, and often these active regions can lead to solar eruptions such as solar flares and coronal mass ejections. I study the coronal heating problem. That is, why is the solar corona so much hotter than the solar surface below it? And we know that it has to do with the magnetic field, which is constantly dynamic and evolving and ejecting energy into the solar corona. And you can really get a sense of that when you watch these Solar Dynamic Observatory movies.